Hi, I'm Alex, and this is Matthew, and welcome to the Old Faithful Geyser.
And we are here today to discuss the geology of how Yellowstone National Park formed.
Matt, before we start, why don't you tell our audience a little bit about Yellowstone National Park and why it's so interesting?
Well, Alex, let me give you a fun fact to start off. Did you know that Yellowstone National Park was the first park created in the United States? And many people argue that it was the first national park created in the world. Geologically, Yellowstone National Park has a little bit of everything for everyone, from the continent's biggest supervolcano for volcanologists to study, to some of the world's most famous geysers for hydrologists, and thousands of small earthquakes per year for seismologists. Yellowstone National Park truly is a scientist's dream. What's your favorite part about Yellowstone National Park, Alex?
I love thinking about the formation of the Yellowstone caldera mat. It all started when a hotspot formed under what is today Yellowstone National Park. A hotspot is essentially an area dominated by volcanism where very warm magma causes rock melting and magmatic ascent. Similarly, at Yellowstone, the hotspot melted the surrounding rocks and created a large magma plume, which then ascended towards the surface, creating like this protruding lump. At Yellowstone, magma from the mantle was basaltic in nature. As this basaltic magma rose, becoming lump-like, it came in contact with the North American continental crust. Some more melting near the surface occurred of like the continental crust rocks, which are very silica-rich, which led to a formation of a different type of magma called rhyolitic magma, which tends to be more dominated by silica. And you can kind of see this in the screen where you have the basaltic magma becoming rhyolitic magma near the surface. After a lot of pressure buildup, the surface of this lump cracked and a huge eruption occurred 2.1 million years ago, throwing 2,500 cubic kilometers of debris into the environment. And this is because rhyolitic magma has incredible viscosity and volatility, which makes it very prone to erupt. And just for reference, Mount St. Helens, there was a huge eruption over there. It expelled only 0.4 cubic kilometers of debris during its 1980 eruption, which led to the tragic loss of 57 lives, but a much smaller eruption. And then since then, two smaller eruptions have occurred at Yellowstone, one of them 1.3 million years ago, and the other one 631,000 years ago. After these eruptions, all the magma exiting the magma chamber then caused the bulge to collapse because it was empty and there was no longer any support. And then this formed what we know today as the Yellowstone caldera, which is a circular depression measuring 56 by 80 kilometers.
I never knew that, Alex. I'm a little bit nervous now to be living on the same continent as a supervolcano. Do you think it'll erupt anytime in the near future?
Well, you can never be certain of anything, Matt, but volcanologists around the world, including the US Geological Survey, are not convinced. It turns out the silica-rich magma chamber that resides under the Yellowstone caldera is only around 5 to 15% molten, which is not likely enough to set off an eruption.
Well, I certainly feel a little bit better now, Alex, although I wish you had said impossible instead of not likely.
Why don't you tell us about your favorite part of Yellowstone National Park to take your mind off the supervolcanoes, Matt?
Sure, I'll start with a fun fact. Did you know that over half the world's geysers are located inside Yellowstone National Park? My favorite part about Yellowstone National Park is the geysers, and why wouldn't it be? It's not everywhere on Earth that giant jets of water erupt into the air. This seemingly impossible feat of nature does have an explanation, though. Whenever it rains in Yellowstone, the water seeps into the ground through the soil pores, where it eventually gets trapped against rocks and superheated due to Yellowstone's legendary geothermal activity. This vaporizes some of the water, which creates upward pressure, driving the water to the surface. Along the way to the surface, some steam is stored in steam chambers, which causes the buildup of pressure. Combined with this buildup of pressure, if the path to the surface is narrow enough, water shoots into the air as a geyser when it gets to the surface. It can also be a trickle if the pressure is not high enough and not enough pockets are available to build up steam. This would instead form a hot spring instead of a geyser, which is not as cool but nicer to swim and relax in.
I faintly remember that geysers usually are surrounded by some sort of deposition. That kind of makes them look like mini volcanoes. Is that correct, Matt?
Yes, good memory, Alex. Geysers are indeed surrounded by a type of deposition that geologists call geyserite.
What an original name.
Water dissolves silica and other minerals when it is moving underground. This is mainly due to the high temperatures of the water. The hot underground water is able to dissolve more minerals, kind of like how hot water can dissolve more sugar than cold water. When this water that contains a slurry of dissolved minerals shoots up to the surface, it cools down because the surface is cooler, and the minerals precipitate out around the geyser. This is how geyserite is formed.
That's so cool, Matt. Do you have any geysers that you recommend to people planning to visit Yellowstone National Park?
Well, you can never go wrong with the famous Old Faithful geyser, which erupts on average 20 times per day, or around every 60 to 90 minutes.
Wow, Matt, I definitely plan on visiting in the future.
Alex, I've been thinking, remember how I said that geyser water flows through tight tunnels carrying dissolved minerals?
I remember.
Well, don't you think that these thin cracks would get clogged from silica and other minerals precipitating out, especially if these cracks are thin and under high pressure? However, this is not what we observe, since geysers are plentiful in Yellowstone and continue to erupt over and over. How do you think this is possible, Alex?
Matt, I'm glad you asked that question because it brings up the topic of one of Yellowstone's most unique geological processes, earthquake swarms. Earthquake swarms are when lots of earthquakes happen in the same area at the same time. And this sort of phenomenon of earthquake swarm both perpetuates the cracks underneath Yellowstone and is shaped by the cracks underneath Yellowstone.
So you mean that the cracks under Yellowstone both create the earthquakes and the earthquakes create the cracks?
Exactly. There are two types of geological processes that drive earthquake swarms, and these are magma-filled cracks and water-filled cracks. You can see that on the image here. The magma-filled cracks here, and then the water-filled cracks there. Water-filled cracks are the more common cause of earthquake swarms because they're much thinner than magma-filled cracks, and they can cause strike-slip earthquakes because the water will lubricate the walls on either side of the crack, and then that will cause sliding to occur. Magma-filled cracks, on the other hand, the magma will separate the two sides of the crack completely, which results in earthquakes that are much more common along the tip of the crack, sort of up here.
That's so cool, Alex. But why is it so important to specify the difference between these two phenomena?
Well, Matt, it's really important because magma cracks and the resulting earthquake swarms that arise from them is a hugely valuable indication of future eruptions, especially if they occur near the surface.
Wow, very interesting, Alex. Looks like we're out of time for today, but before we go, I'd like to give you a fun fact about Yellowstone. Did you know that the rivers in Yellowstone National Park flow into both the Pacific Ocean and the Gulf of Mexico eventually? Thanks everyone for listening, and have a nice day.